So learning objectives: to learn the concept of Markov chain with examples and to learn the applications of Markov network. So models, Markov model, models stochastic system which assumes Markov properties. It is formally represented by a triplet M equal to K, pi, A, where K is a finite set of states, pi is a vector of initial probabilities for each of the states, A is a matrix representing the transition probabilities. Markov model is a non-deterministic finite state machine. So it is a non-deterministic finite state machine. Markov chain. Markov chain refers to a mathematical system that undergoes transition from one state to other as per some probabilistic rules. So it will undergo transition from one state to another as per the probabilistic rules. Markov chain are a way of stochastically modeling a series of events where the outcome probability of an event depends only on the event that preceded it. A Markov chain has a short-term memory. It only remembers where you are now and where you want to go next. This is very important point, that it has a very limited memory or short-term memory, meaning that if you are at this position, then the Markov chain will remember this position and the next position where it has to go. So it only remembers where you are now and where you want to go next. So stochastic FSM, stochastic finite state machine. So the transition matrix is given A equal to this. Now how do you get this transition matrix? This is sunny. Sunny to sunny is 0.42. So sunny is 0.42. Sunny to cloudy is 0.38. Sunny to rainy is 0.20. Next, you have cloudy to sunny. Cloudy to sunny is 0.10. Cloudy to cloudy is 0.45 and cloudy to rainy is, this arrow, cloudy to rainy is 0.45. Next is rainy. Rainy to sunny. Rainy to sunny is 0.20. Rainy to cloudy is again 0.20. This is 0.20 and rainy to rainy is 0.60. So this way you get the transition matrix. If you want to know the probability of the sequence sunny, 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 so you have 1, 2, 3, 4, 5 times sunny. Take initial probability of sunny, that is on any given day, probability that it will be sunny is 0.30. So probability that it will be sunny today, so the probability that today is sunny is how much? 0.30. Probability that it will be sunny tomorrow will be how much? Self loop on sunny to sunny, that is 0.42. So probability that it is sunny today is 0.30, and for you to get another sunny day after that sunny day is 0.42. So by using Markov chain, we can say probability of getting 5 consecutive sunnies is, so today it is sunny, that is 0.30. So one sunny is cut, that is the sunny of today. Now 4 more sunnies you want consecutively every day. So 0.3 into sunny that tomorrow is also, if today is sunny, tomorrow is also sunny, that probability is 0.42. Raised to what? Raised to 4, because now every 4 days, for 4 days you want sunny. So you multiply this, you get 0.909335088. Next question says, first question was your sunny question. Question number 2, what will be the weather be like tomorrow? So if it is rainy today, tomorrow also that it will be rainy, probability is 0.6. So this part is for your tomorrow and this is for your today. So if it is rainy today, tomorrow also it is rainy, 0.6. Rainy today, tomorrow cloudy, 0.3. Rainy today, tomorrow sunny, 0.1. Cloudy today, rainy tomorrow 0.5, cloudy today, cloudy tomorrow 0.3, cloudy today, sunny tomorrow 0.2, sunny today, rainy tomorrow 0.2, sunny today, cloudy tomorrow 0.1, sunny today, sunny tomorrow 0.7. So this is the graphical representation of this. Sunny, it is 0.7, so you did self loop on sunny of 0.7. This is rainy, this is also rainy, 0.6, so self loop of rainy will be 0.6. Similarly, cloudy, self loop will be 0.3, and so on. You will get the chart. Rainy to cloudy is 0.3, so you have rainy to cloudy 0.3, cloudy to rainy is 0.5, sunny to cloudy is 0.1. That means sunny today, cloudy tomorrow. Cloudy today, sunny tomorrow 0.2. Sunny today, rainy tomorrow 0.2. Rainy today, sunny tomorrow 0.1. Let's see the next question. Question number 3. A city is served by 2 cable TV companies, Best TV and Cablecast. Due to their aggressive sale tactics, each year 40% of the Best TV customers switch to cable TV. So today they are Best TV customers, tomorrow they will become cable TV customers. How many are there? 40%, that means 0.4. Today you are Best TV, tomorrow you become Cablecast, it is 0.40. So this is for today, and this is the next year. That is what? Tomorrow. You can consider it as tomorrow, today, tomorrow. So next year and today. So today they were Best TV, tomorrow they became Cablecast, is 0.40. And 60% of the Best TV stay with Best TV. So today you are Best TV, next year also you are Best TV customer, 0.60. 60% means 0.60. On the other hand, 30% of the Cablecast customers switch to Best TV. So today you are Cablecast, next year you switch to Best TV. 30% means 0.30. So today you are Cablecast and tomorrow also you remain Cablecast, will be 100 minus 30%, that is 70% remain Cablecast. They were Cablecast and they remain as Cablecast. So today also they were Cablecast, next year also they will be Cablecast. How many are there? 0.70. This way the matrix is formed. Next is question number 4. Professor Simons either walks to the school or he rides his bicycle up. If he walks to the school one day, then the next day he will walk or cycle with equal probability. So if today he is walking, then the next day, that is tomorrow, this is your today. Today you walk, tomorrow you can either walk or you can either cycle. Walk percentage is also half, cycle is also half. So today you are walking. Initial day is today, next day is tomorrow. Today you are walking, tomorrow you will walk or cycle is equal probability, means it is 1/2, 1/2. But if he bicycles one day, then the probability he will walk the next day is 1/4. Today you bicycle, tomorrow you will walk is how much? 1/4. Today you bicycle, tomorrow also you will bicycle, will be how much? 4/4 minus 1/4. That is 3/4. So today if the professor is using bicycle, then the probability that he will walk the next day is 1/4. The probability that he will walk the next day is 1/4. And if today he is taking the bicycle, then probability that he will take a bicycle even tomorrow is 3/4. This is your matrix. Next question is question number 5. Among 600 cities worldwide have bike share programs. Typically, a person pays a fees to join a program and can borrow a bicycle from any bike share station and can return to it on the same or another day. Each day, the distribution of bicycle at the station changes as the bikes get returned at different stations from where they are borrowed. So the bikes, if they are borrowed from one station, they can be returned to some other station also. For simplicity, let's consider a very simple bike share program with only 3 stations A, B and C. Suppose that all bikes must be returned to a station at the end of the day, so that each day there is a time, let's say midnight, that all bikes are at some station A. And we can examine all stations at this time of day every day. We want to model the movement of bikes from midnight of a given day to the midnight of the next day. We find that over a 1 day period of bikes borrowed from station A, 30% are returned to station A. So you are borrowing from station A, then 30% means 0.3 are returned to station A. 50% end up at station B. So from A to B, 50% are ending up at station B. 20% end up at station C. So A to C is 20%, that is 0.2. So A to A 0.3, A to B 0.5, A to C 0.2. Of bikes borrowed from station B, 10% end at station A. So from B to A you have 0.1. 10% end up. 60% are returned to B. So B to B is 0.6. And 30% end up at C. So 30% means from B to C you have 0.3. Of the bikes borrowed from station C, 10% end up at station A. So whatever borrowed from station C, 10% are ending up at station A. So C to A is 0.1. 10% end up at station B. So C to B is also 0.1. And 80% are returned to C. So C to C is 0.8. How much? 80%, so 0.8. So this way is your transition diagram and transition matrix. So this is your transition diagram. Next question. The matrix shows the probability of transitions between the states at 2 consecutive times. We need a way to represent the distribution among the states at a particular point in time. To do this, we use a row matrix called a state vector. The state vector is a row matrix that has only one row. It has one column for each state. The entries show the distribution by state at a given point in time. All the entries are between 0 and 1 inclusive, and the sum of the entries is 1. For the bike share example with 3 bike share stations, the state vector is 1 cross 3 with 1 row and 3 columns. So for bike share you have 1 row and 3 columns. A, B and C are the 3 columns. Suppose that we start observing our bike share program. 30% of the bikes at station A, so 0.30. 45% at station B, 0.45, and 25% 0.25 at station C. The initial vector will be V0 equal to 0.30, 0.45, 0.25. This will be your initial vector. The subscript 0 indicates that this is the initial distribution before any transaction occurs. If we want to determine the distribution after one transaction, we will need to find a new state vector and call it as V1. The subscript 1 indicates this is the distribution after one transaction has occurred. So what is V1? V1 means one transaction has occurred. One transition has occurred. So this is the distribution after V0. So we multiply V1. We find V1 by multiplying V0 with the transition matrix T. So you got V0, and where is your transition matrix? This is your transition matrix. So multiply this transition matrix with V0, you will get V1. So after 1 day, one transition, 16% of the bikes, you got 0.16. That means 16% of the bikes are at station A, 0.5 445, that means 44.5% are at station B, and 0.395, that means 39.5% are at station C. Using Markov chains to model the weather. A classic example of using Markov chains is in modeling the weather. We know intuitively that if today is rainy, then there is a good chance tomorrow will be rainy too. We might also expect it to be fairly likely to be cloudy with only a small chance of being sunny. We can make similar judgments about tomorrow's weather will be likely if it is cloudy or sunny today. So we can assume, or you can say we can predict what will be the weather tomorrow if today is rainy or today is sunny or today is cloudy. Then we say that likely the chances will be that it will be the same weather tomorrow also. Types of Markov modeler. System is autonomous. System state is fully observable. Markov chain. System state is partially observable. Hidden Markov modeler. System is controlled. Markov decision process. Partially observable. Markov decision processor. Next, Markov chain. Simplest Markov model. System state at time t+1 depends on state at t. Hidden Markov model. Similar to Markov chain, but system states are unobservable. Markov decision process models a system where outcomes are partially random and partially under the control of decision maker. Now, properties of Markov chain is an important question, can be asked. There are several properties that Markov chains can have, including irreducibility. Markov chain is irreducible when it is possible to reach any state from any other state in a finite number of steps. Aperiodicity. A Markov chain is aperiodic when it is possible to reach any state from any other state in a finite number of steps regardless of the starting state. Recurrence. A state in a Markov chain is recurrent if it is possible to return to that state in a finite number of steps. Transience. A state in Markov chain is transient. When you say transient, meaning temporary, something which is temporary is said as transient. If it is not possible to return to that state in a finite number of steps. Ergodicity. A Markov chain is ergodic if it is both irreducible and aperiodic, and if the long-term behavior of the system is independent of the starting state. Reversibility. A Markov chain is reversible if the probability of transitioning from one state to another is equal to the probability of transitioning from that state back to the original state. Properties of Markov chain. A, C and D are recurrent states. They are in strongly connected components which are sinks in the graph. B is not recurrent. It is a transient state. Alternative definitions. A state S is recurrent if it can be reachable from any state reachable from S, otherwise is transient. A state is transient if when we leave the state there is a non-zero probability that we will never return to it. Conversely, a state is recurrent if we know that we will return to that state in future with a probability 1 after leaving it. So means transient means you are never going to return to that state. And recurrent means you will return to that state. That is a confirmation that you will return to the state. Illustration of recurrence or transience property. The chain of the left is such that 1, 2 and 3 are transient. When leaving these points, we can be absolutely sure that we will come back to them or not. So if you see to the chain on the left hand side, we see that 1, 2 and 3 are transient. That means once you have left that state, you are not sure whether you are going to return back to them or not. And 3 periodic, whereas 3 is periodic, whereas 4 and 5 are recurrent. Why? Because you see there is a double arrow. When you say there is a 2 arrows are there, we say that it is what? It is a recurrent. Why? Because when you are leaving these points, you are absolutely sure that you are going to return to them. Sure that we will come back to them at some point. So if you are leaving 5 then again you are going to enter also 5. If you are leaving 4, you are entering 4 also. The chain on the right has one more edge that makes the full chain recurrent and aperiodic. So it has one more edge, that is this edge, which makes it recurrent and aperiodic. A and B are transient states, C and D are recurrent states. Once the process moves from B to D, it will never come back up. A Markov chain is irreducible if the corresponding graph is strongly connected and thus all states are recurrent. So if this is the example, a state has period k if, when leaving it, any return to that state requires a multiple of k times steps. K is the greatest common divisor of all possible return paths. If k equal to 1, then the state is said to be aperiodic and the whole Markov chain is aperiodic. If all states are aperiodic, for irreducible Markov chain, we can also mention the fact that if one state is aperiodic, then all other states are also aperiodic. A state S has a period k if k is the GCD, greatest common divisor, of the lengths of all the cycles that pass via S. A Markov chain is periodic if all the states in it have a period k greater than 1. It is aperiodic otherwise. So all these are definitions of periodic and aperiodic. A Markov chain is ergodic if the corresponding graph is strongly connected up. It is not periodic. Ergodic Markov chains are important since they guarantee the corresponding Markovian process converges to a unique distribution to which all the states have strictly positive probability. Conditional independence. Any two parts of Markov network are conditionally independent given evidence that blocks all paths between them. More formally, there are three key properties of Markov networks related to conditional independence. Energy functions. Joint probability in a Markov network is frequently expressed in terms of energy functions. Maximizing probability P of Px is equivalent to minimizing energy Ex. So this is a difference between Bayesian network and Markov network. Directed, undirected dependencies can be modeled. Not all dependencies can be modeled. Cannot assign a conditional probability table to each node and apply the chain rule. Since there are no parent-child relationships in Markov network, we cannot assign a conditional probability table to each node and apply the chain rule as we do in the Bayesian network. Bayesian version of this captures the conditional independency of A and C given B and D. B and D are conditionally dependent given C. Cyclic dependency structures easily represented in Markov network.